Hello, everyone, and welcome to the future of design engineering. I'm Anthony Kapkin, interim editor of Design Engineering, and your host for today's session. My predecessor, Andre, has assembled some truly inspiring industry experts who will discuss applications and research, basically just really cool stuff in the areas of CAD, robotics, and metal additive manufacturing. Uh, Now, there will be time here and there after each speaker to ask some questions, so don't be shy. Just use the question tab to ask your questions, and we'll get to as many relevant questions as we can. The session is being recorded and will be available for viewing later. Now, enough of me. Let's bring our first speaker on. And you're going to enjoy Mark. Time to bring out our first speaker. So Mark's career and education span MIT aerospace engineering, CAD/CAM programmer, Formula One parts maker, Renishaw, University of Waterloo's multi-scale additive manufacturing lab, to where he is currently, leading Tronosjet's additive manufacturing aerospace programs. Please welcome Mark Kirby.
Okay, excellent. So I'm going to spend 10 minutes on my top 5 things that I think are exciting about metal, the future of metal printing. These are my opinions, Mark Kirby's opinions. I do work for Tronosjet, but these are just my opinions, not those necessarily of the company I work for or any of the previous companies. But we'll try and start with some facts, shall we? So this is, of course, the Wohlers report, and we're selling about. You're going to remember the number 2. It's about roughly 2,000 machines a year. Metal machines, metal systems are being sold every year, and I started in metal printing about 2013, and we've gone from about then maybe 400 machines, and now nearly 4,000. So we've seen an order of magnitude increase in the number of machines that are being sold. The famous song 50 Ways to Print Metal, it's about 20 different ways that you can print metal. And if you expected me to pick my favorite way of printing metal, you're going to be disappointed because that would be like trying to pick my favorite child, isn't it? And you're not allowed to do that. And I actually don't think it's important how we print metal. What do I think is the problem? It's not that we have too many machines, too many ways to print metal. It's actually we've got too few. If we're seeing 2,000 machines, 20 different ways to print it, there are about 200 companies doing it. Maybe we're seeing sort of the order of 10 machines per company, very, very roughly 10, maybe 100. It's just too few. So what is stopping the adoption of metal printing? Well, I think there are better ways of making things. So what do we need to do to compete? Well, we need to offer more value. That's typically about going faster, but not being more expensive, because time is money. So one way we can go faster that I am excited about, and thank you for Enlight for sharing these slides, is what's called beam shaping, because we want to put more power in. We need more lasers. We've already got machines. We started with 1 laser, 4 lasers, 8 lasers, 20 lasers. That tends to sort of bring some diminishing returns. And of course, every laser does add more cost. Beam shaping is a way to put more power in, and the physics of melting the material probably require us to do this. So again, these are some slides, and I always kind of come back to subtractive machining because that's where I grew up, and this is a bit like, well, I have different cutters. I have roughing cutters, finishing cutters. We'll be more elegant in the way that we build material. So beam shaping, I think, is certainly something you should look out for. And these are the figures that are being quoted to reduce the cost. This is, I'm not going to make any claims for this. Clearly, they can go faster. Here's some times that are being produced, so we're going faster. But if I go faster with a much more expensive laser or lasers, then I haven't really achieved anything. But I think that beam shaping is likely to give us another order of magnitude improvement in productivity. I haven't quite got an order of magnitude here, but I started in 2013, 10 centimeters per hour was about the standard there. We've gone to 100 and 1,000 cc's an hour, so 2 orders of magnitude in 10 years in terms of the speed with which we're going. That is more, typically with more lasers. So we've got, will technology, will the hardware give us another 1 or 2 orders of magnitude? I certainly think it will. I'm not a material scientist, but we can do lots of fancy things as well with beam shaping. If you are a material scientist, that would excite you. On to my next thing that I think is exciting. This is actually the bracket. This is a bracket that Tronos has produced. It's actually licensed to fly by the FAA. It has a PMA, but it's made from powder. And what is the problem with powder? It's too expensive, simply too expensive. And if we use 10 times less material, but it costs 10 times more per kilogram, and I still don't go very fast when I print it, I don't have a great business case. I'm really excited about what you're going to see next, which is a bit of machining to produce powder, courtesy of Metal Powder Works. I'm just going to play their video. Okay, so why am I excited about that? Because I can see if we just stick a bar of material in a lathe and we can produce our own powder, and it works, and it really does work. There was some skepticism about whether metal chips are very good for printing because they're not spherical. There's quite a bit of evidence that actually the fact that they are more prismatic leads to better absorption of the laser energy. They're very, very consistent. And it's a cheap. Fundamentally, it should be a cheap way of producing powder. So I'm quite excited about that development, because I think you're always going to be stuck with the cost of your raw material, no matter what technology you use. So that's kind of one of the limit cases that we come to. So cheaper material is certainly important to wider adoption. What's the next thing on my list? Well, directed energy. Let's go. So we want to go faster, but let's go bigger as well. There's a trend there, and powder bed probably only gets us so far, only so sensible to going bigger. Directed energy, which is where we sort of weld material on the end of probably a robot, lets us produce something quickly, like the block you can see in the top of the screen, and then maybe the robot can, and I very much hope our next speaker Max is going to tell us about how robots can be even more useful than they already are, that we can produce a finished component and we can inspect it and we can scale it. And I'm going to lead to my next slide, which is a sort of image of a robot, a humanoid robot. What are the limits to production? And I am plagiarizing somebody here, but what are the limits to production when we have, it's normally GDP, isn't it? When our population could be potentially infinite with robots, they're working 24/7. What happens about things like learning curves, that we're so used to in manufacturing? when now is our learning curve just one unit with, with maybe AI, and we can transfer the learning instantly to everywhere. What's that going to do to the future of making things? So this is a design engineering broadcast. So obviously we've got to decide exactly what we are making. But I think the future is incredibly exciting in terms of what robots will do for us, what AI software will do. I actually think that the next two speakers have far more influence over how successful we're going to be. The question for me is how the human fits into the loop, where we fit into all of that. But I won't steal their thunder. I'm going to finish with, I don't think I made my top 5. I think I only made my top 4. But we do often take our material. Once we've printed our metal, we need to show that we have indeed made good metal. So we tend to print lots of tensile coupons, like in the bottom left, and then we tend to pull them apart. And I want to play you the next video, and I want you to imagine that the potato is in fact a tensile bar, and I hope this makes you laugh.
On your last trip, did you discover what the Earth people eat? They eat a great many of these. They peel them with their metal knives, boil them for 20 of their minutes. Then they smash them all to bits. They are clearly a most primitive people.
Anyway, I hope that was funny. So yes, we do smash all of our things to pieces. So is there a different way of doing it? This is the last thing that I've got. This is a company called Plastometrics. And instead of smashing things to pieces, they're carefully indenting something, and they are figuring out the stress strain curve of the material by measuring the indent that's produced. So let's just play that little video here. I think this could be really quite exciting to reduce the costs, particularly in regulated environments where we absolutely have to prove that the material we've produced is up to spec. Okay, that was my quick 10 minutes of the top 5 things that I think are exciting about metal 3D printing, and hopefully it's going to be a nice lead in, Anthony, to our next speaker. So thank you very much.
I think it actually will be a fantastic lead in, and thanks for sharing the top 5. There's some really cool stuff there, no question. And thanks, Mark, for taking the time. But yes, let's now switch it on over to our second speaker. It's a nice segue. So our second speaker is education and career, includes a master's degree in aerospace engineering from Politecnico di Milano, Master of Science in Data Analytics, and a Master's of Engineering in Robotics, to his current role as Chief Executive Officer of Xaba. Please welcome Max Moruzzi.
Awesome. Thank you very much, Anthony. And thank you, Mark. A very exciting presentation as usual. Like I said, I love your energy. And so Max Moruzzi, I am the co-founder and CEO of Xaba. Xaba is a Persian word meaning imagining and transforming data into reality. So that's the reason of the name. That's why I called the company like that, because it captured my DNA and the DNA of the team that is working for me. And so what is the vision of Xaba? Very simple. We want to harness the full power of generative industrial AI in order to deploy to the industrial automation, robotics, and more than that one, what we call the cognitive control. So in essence, we want to replace industry giant like Siemens, Rockwell Automation, Schneider Electric, Beckhoff, and ABB, because we think that the age of control that are just empty box where companies have to spend thousands of hours in order to teach the machine what to do or to program the production line, which it takes maybe even years, I think is gone, okay? So, and certainly that's our mission. So we don't want to just evolve automation. we want to revolutionize it. And with that, just a little bit about our background. That's what my team and myself had the opportunity to do before creating Xaba. So major project for automotive. Mark was mentioning something about 3D printing. What you see there on the one of the pictures is a bracket for General Motors done with an AI system that we were designing in San Francisco. So the AI designing the shape, not the human, and then the machine having an AI on board in order to print that one. That went in production. Then you see the spaceship for NASA JPL that will go to Europa, one of the Jupiter moon. Everything in that case has been done by a synthetic brain. The human defined the problem, like Leonardo da Vinci would like to say, okay? A problem well posed is going to find a solution. But I think we forgot that one, and we're trying to jump on a solution rather than properly define the problem. And so we want to reverse that one a moment here. And so my team, again, is a composition of AI scientist, mathematician, and mechatronics. This is one of the technology that I'm going to talk to you today. So I'm going to run a short video.
Imagine a world where robots are equipped with a cognitive brain, enabling them to autonomously generate programs from simple to complex tasks in minutes rather than weeks or months. Introducing Xcognition, the revolutionary AI-driven system that automatically generates robotics programs. Compatible with any industrial robot on the market, Xcognition works seamlessly with both old and new robotic systems. With Xcognition, you can generate programs automatically 10 times faster than traditional robotics programming software, saving you not just hours, but significant costs. Xcognition's proprietary generative AI platform breaks down barriers like robotics programming skills, part-to-CAD variances, and precise trajectory generation, making robotics automation fast, scalable, and accessible for everyone, from small shops to global corporations. But that's not all. Xcognition transforms a single robot into a versatile work cell, automating multiple tasks, from welding and deburring to drilling, machining, painting, and polishing. Step into the future.
So this is one of the technologies that I'm going to discuss during this presentation, which in essence, what is Xcognition? Xcognition and how we are positioning Xaba, we like to think that we are what is OpenAI for the general, let's say, public. We are the OpenAI for industrial automation. So in essence, it's a synthetic brain. It's a synthetic brain composed of not just a copilot AI, but what we call as well a strong data ontology and knowledge mapping that enable, in essence, Xcognition to really provide the brain that a machine, that automation needs in order to drop the barrier that are actually in the fields today, preventing automation to really explode, okay? And so here you see, in a nutshell, some of the technology that we're developing here, okay? So it goes from capturing legacy data to assisted reinforcement learning, to deep learning, to data ontology, to knowledge mapping. This is what really composes a synthetic brain, very similar to a human brain. I'm super passionate about neuroscience, and that's exactly how I'm architecting Xcognition and all the technology that you're going to see. So what is the ultimate goal for us? The ultimate goal is basically that you are just submitting a test, you are talking with the machine, or you're submitting a drawing, and then the brain has the know-how in order to transform your dream to reality. We're already doing that one for some of the applications that I'm going to show to you, but that's exactly why we're making the claim. Again, this is not a copilot AI. This is a strong physics knowledge mapping engine that augment, in essence, operator programmer company in order to adopt the automation and to scale it. Then moving forward, you see some of the example here. So on the top one, you have, in essence, our Xcognition platform that is not even receiving a CAD model. It can work with vision system, retrieve the real geometry, leveraging point cloud, CUDA from NVIDIA in order to be super fast, and then transforming that one in real application. Like, for example, what you see on the right is a quality inspection system where the AI has extracted all the features automatically, created the program, removed the singularity from the robot. At the bottom instead, you have the welding. The AI system take care even to compute the voltage, the amperage, the speed in order to have a very high performance welding system like you see here, okay? And so a technology, for example, like welding that has been perceived like a craftsman, okay? So only some expert can do it. In reality, you know, an oscilloscope together with a fast Fourier transformation turns out to be that can teach to a synthetic brain how to do an operation like that one. And now there are 400,000 vacancies just in the US for welder. Company cannot grow because they cannot hire that kind of expertise, and university are not producing that one. So that's one of the reasons why, you know, technology like that one, we're getting a very good momentum, and we're looking to address a real problem. And that's one of the aspects why we are developing what you see today. And so let me show you a little bit more. Again, today we have limited amount of time, but one other technology, one other fields where we're applying our synthetic brain is in aerospace. I cannot show you the real part, but this one is a wing, 20 meters inside of composite material. And the synthetic brain is controlling not just a robot, but a swarm of robots working together, okay? Doing operation like drilling, fastening, QA on the fly. Again, this is not the problem in the hardware, okay? The point, the hardware has been always very capable. The problem was always in the control. The control is what is creating the barrier, difficulty to program, difficulty to get the quality that you want, and not capable to reach the productivity or the utilization that you want. That's why we did not focus to create another robot, but we focused to create a real brain that in essence can enable the hardware to work together and to really exploit their potential. And so another application that I want to show to you today, how the AI is actually changing, you know, manufacturing. For example, machining for aluminum casting. There is a humongous interest in aluminum casting right now in automotive and in other sectors, dictated by, you know, disrupting process, for example, starting by Tesla with the mega casting. The problem is that when you have a casting, the CAD model doesn't exist anymore. And so the old fashioned to go on a CAD system and to program a machine and to deliver the actual instruction is gone. You don't have it, okay? And if you want to program in that way, it will cost you forever. It will make impossible for some of these very high energy, quality, sustainable process to actually fully nourish, okay? And so that's why we're doing this technology, because if you have a brain that can connect with the vision system, understand the real geometry, program your machine because it has the physics behind, that instead becomes a valuable process, okay? Enable that process to happen in the first place. Let me move to the next slide. And so here is instead another project that we are automating for the rail car industry. Again, a similar situation here. When you have to manufacture a rail car, you have to deal with the fact that you have 20-meter aluminum panel with a lot of distortion. And again, the CAD model is just a mathematical abstraction, like the CAD representation of your robot. It is not true. You need to capture the physics, the elasticity, the distortion, if you really want to automate the process. That's why ChatGPT cannot do that one, okay? That's why you need a multimodal data set and knowledge capturing system behind in order to transfer the know-how from what you want to do, which in this case is the manufacturing, machining, and grinding of a rail car, to a robot that enable that operation to happen and to happen in an automated fashion. So in a way that you can scale your production and you can have you know, the ROI, the sustainability that everybody is looking for. So for example, this operation today is done by hand, like the drilling that I showed you before in the aerospace. 80% of the aerospace drilling still by hand with mask, because robots don't have the capacity to do it, not because of the hardware, because the brain cannot control the accuracy, the position, the location, and so. But if you empower the system and the physics with the real brain, then even the robot can tell you more of the story that they were unable to do until today. Then I want to show you something different. The same brain now is controlling a gigantic AI distribution and logistics system, in the same brain that we're developing for a welding, for a machining, for a riveting that I showed you before. Now the brain instead is controlling, let's say, several hundred feet of facility, which are distributing different kind of goods. So in this case, the AI is commanding a gantry machine, AGV system, robot, in order to do hybridization and palletization and minimizing, let's say, the number of, let's say, travel that you have to do in order to deliver your goods. And the system is dynamically understanding the recipe, okay? What is changing? The demand is different. We have to come up with a different combination, or now there is a different request. And so the system is capable to adapt in all of that, and it has a fantastic AI combined with genetic optimization, what you see here, in order to enable hybridization in pallet, which is one of the big quests, even from Amazon, okay? How can I pack something different than just similar boxes inside to a container? So in essence, we are applying the brain in order to really have a huge impact in warehouses that today are used very inefficiently, always at the maximum throughput, because people and companies do not trust to lower, for example, the speed of the conveyor. So they are consuming a humongous amount of energy simply because there is no a trustable brain on top of that one that can guide the factory to be extremely much more sustainable, extremely much more, let's say, efficient and productivity rate as well. So moving forward, because again, we have limited amount of time this morning. Okay. So I told you about energy cost. So when you have a brain on top of a machine, on top of your production line, the brain is capable to understand as well the power that you are actually consuming. And believe me, some of the case study that we're doing with some of the major automotive, both in the US and Europe, is tremendous, the amount of energy that today they are wasting. This is a report from KUKA that you can find on the public sources. 39% of the cost of any production line in the automotive is dictated by the energy that the robot is actually consuming in order to do that, or not by the maintenance, not by the capex cost. The majority of the impact is the energy that that machine is consuming during this life. And just by applying a brain and actually understanding among all the trajectory what is the most efficient one or how to position that one, we were able to show major change, major impact, how robot, how AI, how true physics AI can in essence change the shape of automation in several aspects. Then we're doing more, okay, because this is a complete brain, and a brain is made at least of two components: the cortex, that is the one that I show you up to now, so the capacity for you to communicate with the machine and then the machine to generate a task. But there is the deep side of the brain, the one that in essence control your muscle, okay, and transform that one from an instruction to an actual action. And so the other part that we develop in Xaba is this one.
DLC programming has long been a tough, time-consuming challenge. It demands highly skilled professionals, seamless system integration, and countless hours spent debugging and maintaining automation lines. Today, programming and deploying PLCs still account for a staggering 80% of the total cost of programming automation lines. Little progress has been made to ease this burden, until now. Meet PLC-Fi, revolutionary software powered by generative AI. PLC-Fi is transforming how machine builders work, reducing the time needed to select, configure, program, and deploy machine components by up to 50x. With PLC-Fi, you gain powerful insights into parts interoperability, costs, lead times, and energy consumption, empowering smarter decisions and faster processes. Leveraging multimodal data models, PLC-Fi processes both text and images, seamlessly interpreting functional specifications and schematics. Its data ontology modules build custom knowledge bases, automating relationships, attributes, and hierarchies for any unique setup. Rule-based modules generate PLC code that is not only syntactically precise but also semantically accurate. PLC-Fi goes further by generating industrial PLC code compatible with Codesi's protocol, enabling seamless interfacing with leading industrial controllers from ABB, Schneider Electric, Siemens, Rockwell, Bosch, Beckhoff, and more. With continuous learning, PLC-Fi evolves with every interaction, delivering smarter.
And so this is the other side of the brain. So at this point where we think that we completed really the synthetic brain for automation, because now we can not just automate the generation of the task, but we know exactly how to enable the machine to auto-program themselves or the production line in order to get the efficiency that we want or the functionality that we want out of that one. And like is highlighted here, 80% of any machine vendor for oil and gas industry, warehouse for Amazon or Walmart, crane or anything like that one, they are going through this kind of hurdle. That's why automation today is still, very minimum adopted with a lot of, okay? And so moving forward, I want to show you exactly what that means, having that situation. So in this case, we are enabling company in essence to just say, listen, I have a functional spec. I desire to have a machine to do that one. And then I would like to not only insert the intelligence that will make that line, that machine alive, but even the capacity to select and to all the components that are actually needed. And so as Cognition is capable to read a human written functional spec or an electric schematics, for example, and then tell you exactly the component that you need, guide you about, okay, what kind of energy consumption you have, lead time, and all of that. But then it's generating as well the PLC code that today is the number one barrier that is preventing machine to be more efficient, because it's impossible to find, for example, a PLC programmer that knows how to code a fast Fourier transformation into a PLC code without naming other physics and mixing, motor, actuator, or anything you have in mind extremely much more efficient. Right now, we have almost 500 million of industrial controller in the world, controlling everything you touch, from your car to the elevator to the crane to whatever, you name it, is controlled by an industrial PC. The way that they're actually controlling the actuator, the motor, and so on is extremely inefficient, but not because in the capacity of the PLC programmer, but because a human cannot code in the way that an AI system can actually do, using this multimodal data knowledge in order to do that. And so the impact could be really significant in that sense. And now, obviously, Mark said it, so we're moving toward as well to humanoid. The challenge in the humanoid is not so much the humanoid itself, is how do you program the humanoid to do something useful rather than moving a box or jumping or running. That's all good, okay? But our quest is different. Our quest is we want to have a humanoid to be able to mount, for example, a gearbox system, okay? Just to name some of the things that we are testing, or to actually perform a welding, or to actually perform a drilling, not really moving a box or running, with all the respect, okay? That's not our quest, okay? And in order to do that one, you need to have a physics brain, okay? It's a completely different game. And then I want to close with some other project that we have done. So the slide that I showed you before, we have project for real. We have very, very interesting customer, both in North America and in Europe. And one of the projects that we have done early on as Xaba is in the 3D printing aspect, so massive additive manufacturing machine in order to 3D print a full functional car chassis. This is the only chassis right now in the world that in essence is combining polymer and metal, and is fully functional because the car has been fully done, not just a plop of material, but a functional car. And that machine was fully driven by our AI control brain, because otherwise it would have been possible with the technology today. Pick any software you like, pick any aspect that you want, it would have failed, okay? Because the system is so incredible non-linear in terms of process parameter that goes beyond what you can actually program with current and traditional methodology. And so the AI here selected all the process, drive all the machine point to point, put all the knowledge into that one. That one makes it possible for us to build this car chassis in 3 components, spending 35 kilowatt of energy rather than the 700 that at least any car around the world today is consuming. So that's another aspect of what the AI can actually do there. And I'm going to close with that, in essence, show some of the things during the process of that. And I'm showing this one because all of this activity has been done, as using Canadian, let's say, resources. And Anthony, I think is good for me. And thank you for the opportunity to actually share with the audience today what we are doing in the field of generative AI and how we see generative AI, truly physics generative based AI, impacting the automation. So
Oh, that was fantastic. That was a real eye opener with a lot of things. Only Max, I wish you had brought a little more passion to that conversation.
yeah, exactly. Exactly.
But actually, before we move on to our third speaker, I wouldn't mind asking a question. Just looking at X-cognition and PLCify's ability. Just a question that came to mind is, so with PLCify's ability to, autonomously generate the PLC code, X-cognition's cognitive control, empowering machines to self-adjust. I think you've given some examples, but how do you see those two combined, those two parts of the brain, transforming industries that have long relied on manual programming?
Yeah, exactly, Mark. So there are 2 aspects here. One, again, if we look at in 1957, Unimation introduced the first robot for General Motors, okay? So more than 6 decades ago. The number of robots today, for example, if I'm picking that one as an example, there are 4 million industrial robots around, so none. If you look at the number of PC and control, none. The reason is the traditional way, the manual way to program that one is very costly, very expensive, and not the best way, in essence, to approach that particular problem, okay? Technology like S-Cognition prevent that barrier. So that means that anyone is a democratization. Anyone can approach that machine and discuss, like me and you were talking, in order to have the machine doing exactly what you want, with a game, with a difference as well. If I use the example of AlphaGo, AlphaGo back in the day, beat the famous chess player. Okay, now today there is not a single professional chess player that is training himself with another human. Is actually training with an AlphaGo system, because both of them are growing. And so that's my other point. The impact is going to be that this technology is transforming manufacturing from being a job to a career, which is the other problem that we have today. Companies are struggling to hire talent because, to be honest, who wants to study, let's say, engineering and then later on having his face burned 8 hours on a day by a welding gun, rather than instead working with the machine and seeing, oh, that wave signal, that fast Fourier transformation, that logic, that tactics can, in essence, enable now a new process. That one is extremely rewarding for the machine and for the talent and for the company, ultimately, that they will be able to attract talent. In regard to PLC-5, instead is massively even bigger, because as cognition, I give you the example on the robot, but now there are 4 million robots in the field. There are an alpha billion of industrial controller today, where in essence are extremely, let me use this one, I know that I'm going to sound maybe unpolite, but they are very dumb, okay? The best way that they have to control a motor, for example, is through a step function or a ramp function. Nothing is optimized in that direction. The amount of waste, the amount of inefficiency is humongous. As a matter of fact, 80% of the cost of any production line for oil and gas, energy, warehouses, consumer, is in the programming of this PLC. Okay, another example, you have an industrial crane in the middle of Toronto that is moving a load, and then all of a sudden there is a wind gust, and then you have to stop because the load start to swing. Or, for example, when you are welding for a shipbuilding, one of the case study that we did with the PLC-5 is enable the system to understand the problem, and so for that to insert the knowledge that automatically and in real time enable the AI to compensate for that effect. That one is called coding a double pendulum equation into a system. And where are you going to hire someone that has that kind of capacity? By doing that one, now anyone can move that crane, any operation of that one can actually happen. And so that's why I'm saying this technology will take people to a different level, enough to deal with, this spline, it doesn't close, and then you have to waste humongous amount of time to script something for either, I don't know, a Siemens, a Dassault, SolidWorks, an AutoCAD platform, and you are wasting your life in that direction, rather than be able to communicate your dream with a machine that now can, in essence, do a rewarding exchange with you, okay? So that's how they are reshaping. Increasing the democratization and utilization of automation, because we are removing all the barrier. But the other thing that I think, my opinion, is very, close to the core why we're doing this one, is transforming manufacturing from being just a job to a career, okay? And that to me is extremely rewarding.
No, you had some excellent examples, and thank you for that answer, Max. Just thinking about personnel, you had mentioned near the top. I think I might have written it wrong. This is a huge number, 400, or was it 200,000 job openings for welders alone?
400,000
For
just in the US. Company cannot, and that's why on customer that we have, they cannot scale their business. They have business because there are 400,000 vacancies just in the US for welder. That's a fact.
Simply amazing, simply amazing. Max, I'm going to let you go, and I'm going to bring in our third speaker now, so that we definitely give Elissa enough time. So again, thank you, Max Moruzzi with
Thank you.
Xaba. And now, last and most certainly not least, we welcome our final speaker, CEO of Metafold 3D, Dr. Elissa Ross. Drawing on her background in mathematics and industrial consulting, Elissa leverages geometric principles to enhance product performance through computational design. Her company, Metafold 3D, makes a 3D geometry toolkit to solve a variety of challenges in digital manufacturing. Please welcome and take it away, Elissa Ross.
Amazing. Thank you so much, Anthony. And thank you, Mark and Max, for truly inspiring talks. These are tough acts to follow, but I'll do my best. And, in a funny way, I think we maybe have the order slightly reversed here in the sense that I am going to be talking about things that we need to address before we get to manufacturing, before we get to 3D printing, robotics, or actually making anything in the built world. And that, of course, is CAD, is design, and the topic that's closest to my heart, which is geometry. So yeah, I'm going to be talking about Metafold's work in manufacturing, specifically our toolkit on geometric intelligence, what that really means. But before we get there, I want to begin with a slightly philosophical maybe question or provocation about CAD, which is this quote. And you've probably heard something very similar to this. So it says, "We shape our tools, and thereafter our tools shape us." This quote, actually, interestingly, is often attributed to Marshall McLuhan, and arguably this is precisely his idea. But in fact, it was John Culkin who wrote these specific words. And this has been a fascination of mine throughout my life, really, is how the tools we have to design and make things actually shape what gets produced. And maybe I'm going to date myself here, but to go to an early example, in my childhood home, we had a very early Mac computer, which came with this Mac Paint program. And I spent endless hours drawing pictures just like these. Something about that brick pattern absolutely speaks to me. But the point was, everything kind of looked the same. We knew it came from Mac Paint, no matter how much I tried to kind of vary what I was doing, it always had this certain look to it. And this is, of course, true more generally, that the tools we have to design things in our world, they actually determine what we design. And so in a lot of ways, our vision at Metafold is to give engineers and designers the most expressive tools to create things. And that begins with geometry. So before we dive into those details, I want to talk a little bit about manufacturing. And Max set this up brilliantly in his discussion of the wasted energy in manufacturing. There's a huge cost to waste in manufacturing. We tend to think of this in terms of material waste. In fact, there's so much more to the concept of waste. By some statistics, 20%, fully 20% of every dollar spent in manufacturing is just kind of burned. So material waste, obvious, energy waste, Max talked about that. At Metafold, we are really focused on these two at the top, time waste and knowledge waste. And these are really kind of things that I think come up very early in the design process, and something where we can have a big impact. The second kind of point, just for context, I want to make is that, like all data in the world, which is increasing at this astonishing rate, 3D data is exploding. And this is, this graph is kind of, you should interpret this as really a story. It's a story of value. And the question is, what parts of 3D data have the most value? And I would argue that the engineering and CAD data is very valuable as a percentage. This is not necessarily like file size or quantity, but in terms of percentage of value, I would say that this is really quite a large segment because it has such a direct impact on production and on safety. So building on this, manufacturers need to use 3D data every day to make important business decisions. They start with CAD, they need to assess it in some way. They need to decide, a variety of things. So for example, a contract manufacturer might want to answer these questions. How much should this part cost? How much does it cost to produce this? Or even more simply, what manufacturing process should be used to make this part? If you kind of hand me a CAD file, can I tell you if this is a CNC part, a sheet metal part, an additively manufactured part? It's not obvious. In the more design side of things, in aerospace, actually both previous speakers talked about this industry because there's such an attention to detail, to innovation, and to sustainability in this industry. So one of the key questions here is how much material can I remove from this part? Something I will come back to a little later. But more broadly, are there other parts in my whole catalog of parts that we produce? Are there other parts that are good candidates for material reduction and redesign? And finally, in sportswear is an industry because they have such pressure to innovate and actually fewer restrictions, like aerospace, which is a highly regulated industry. Sportswear has a lot more liberty, I would say, but nevertheless, they're under tremendous pressure to innovate, to come up with new designs and new engineering. So Metafold, our business, is shaped around supporting a very knowledge-rich approach to manufacturing. Geometric intelligence is a toolkit for making sense of 3D data, for converting 3D data into information that we can use to make decisions, to do data science, and that will really inform, a critical business direction. So specifically, the three real applications of our technology are the analysis to analyze existing parts for manufacturability or some kind of feature detection. We help our customers develop custom CAD tooling to support their manufacturing process. You can think of this as like a digital tooling. And then finally, and maybe the thing that's most relevant to today's talk, is we help our customers design very performant parts. So let me give a bit more detail on these three use cases, beginning with this application to contract manufacturing. So we work with high mix, high volume manufacturers who their goal is really to take a CAD file and say as much as possible about that CAD file without having an expert engineer open it up, spin it around, take measurements, and so on. And Metafold is unique because we have this API that we can use to do this geometric analysis. So we can do the feature detection that you're seeing in this image here, and we can process thousands of parts per hour so that this capability, this geometric analysis capability, can get baked into the analysis pipelines for these high volume manufacturers. So that's really on the analysis side. I won't focus too much more on that. We also help customers develop commercial and internal CAD applications. So this is an example. One of our customers, General Lattice, they're a nice startup in the additive manufacturing space. They have this digital materials platform, which is really cool. They've built a ton of IP around validating different structures to be thought of as materials. What they did not want to do was develop their entire CAD kernel or geometry kernel to support the delivery of their IP and the commercialization of their IP. So they licensed our geometry kernel, our cloud-based geometry kernel, so that they could very, very quickly develop their application and convert their valuable IP into something that they could make a profit on. This use case is also relevant for large manufacturers who need a lot of customized tooling for their own manufacturing. We see this a lot in different industries where there might be a kind of CAD workflow that probably lives inside one person's brain and that really should be accessible to more team members. We can help make those things more accessible by developing custom functionality and packaging it up in a way that's really easy to use. But where I want to get to right now is really on the design side. And at Metafold, we're very passionate about reducing the lag time between design and simulation. So in a traditional approach to this problem, you would often have someone doing a design, sending it to engineering or converting it into a file that can be submitted to a simulation solver, and then waiting for the results and then going back and iterating on the design. This is super slow, and we believe it can be much faster, which is why we really love this design of experiment approach. So with Metafold, you can set up effectively an experiment where you take different geometric parameters and do a large-scale simulation of those structures all at once. And you can see the information all together, and you can use that to inform your decision making. Now, this happens to be a sort of lattice structure, like you might want to 3D print, but this is absolutely not restricted to lattices. And we do this for all kinds of different parts and different geometric variations. The bigger point is that there isn't really a good method for doing this right now. And so we really love this approach, and we believe this gives people a lot of tools to make good decisions. A different approach might be topology optimization. Some people are very familiar with this idea. Topology optimization can be quite nice. However, it does give you one answer. It gives you one solution, which might be locally optimal, but might not be globally optimal, which is why we advocate this more broader sweep approach. So I want to show you an example, I think we have time, of a case study we did. Really, you could think about this relating to heat exchange, but it can be thought of more generally anytime you have a trade-off between surface area and pressure drop. This comes up in heat exchange because heat exchange happens over a surface. So the goal is really, let's maximize surface area. At the same time, you still want to maintain the ability of fluid or air to flow through. So this question, what structures maximize surface area while minimizing pressure drop? We approached this in this 3-step way. So we used our Python SDK to generate a very large data set of structures. We connected this with an open source CFD library to run a flow simulation. And finally, we used the design of experiment approach to kind of zoom in and find some greater detail. I really like the results of this. The steps 1 and 2, so creating the data and then running it through the simulation, you can see we get this nice distribution of forms. So surface area is on the bottom here and permeability is on the side. And so we're looking for structures that are, maximizing surface area while also maximizing permeability. We still get a lot of flow through them. And what I like about this is that there's been a lot of attention paid in the additive manufacturing community to structures like the gyroid, which is very cool. It's not the only one. And in fact, we found that these spinoid structures, which are more kind of natural looking, I suppose, more organic, more random, they actually perform better in this setting. The last step in this study was to do a kind of zoom in. So we took 2 of the high performing structures. I think this Schwartz P up here and this spinoid one, we took those 2 and we blended them together. And this is all super easy and possible because of our foundational geometry technology. So we generated very quickly these structures, and then we were able to run them through the analysis again. And so what we found is that the previous graph area is shown in this region here. And through that design of experiment, we kind of exploded that space of good candidate structures. So this highlights, in a way, our approach to these kinds of design problems. It's not a solution where you dial in your parameters and we give you the answer. We give you tools to apply your expertise to these problems, and we convert 3D data really into information that you can use to make decisions. So I'll conclude here with this little graphic. Metafold, we support this knowledge-rich manufacturing. You can think about traditional manufacturing in this way as having very limited data flow between design, between prototyping, and production. And this leads to higher waste and lower profit as people, need to fabricate more and test things, and just, take much more time in these cycles. The Metafold way, applying geometric intelligence, we do far more digitally. There's great data flow between design and simulation. This leads to a very, very informed validation phase where you get to physical production with a lot of information. And there's huge opportunity here to reduce waste across the board, and for higher profit, of course, and higher sustainability, I should add. So, maybe coming back to this quote again, we shape our tools and thereafter our tools shape us. Geometric intelligence, this is our answer to this concept. How do we create the most expressive and flexible platform for CAD? And this is our vision that by giving access to new ways to represent geometry, we're able to give new powers to designers, engineers, manufacturers, and super excited about that. So thank you for that, your attention, and happy to close with a couple questions if there are any.
Oh, that was just brilliant, Elissa. Fantastic. I love that example with all the different geometric shapes, and the fact that you point out that uh, it can provide possibilities, but it's still up to the design professional to, weigh those possibilities against their own knowledge base. And anyway, it's clever. It's just clever. I cannot see how it doesn't save on that 20% waste you were talking about right at the beginning. I have a couple questions for you. I'm just looking at the clock, but I think we've got time for two questions. But we'll see how it goes. I was just thinking about Mark's conversation and then Max, and then also what we just learned from you. How do you see artificial intelligence and machine learning intersecting with geometric intelligence, in the coming years?
Yeah, I think we're at a super interesting point. And I'm like a little hesitant to say anything about AI right now, but we're at a super important, interesting inflection point in technology in general. It's also quite distracting in a sense because I think a lot of people believe that, like LLMs, we might just be able to kind of type into a chat bot, the part that we want, and it comes out optimized. This is really not true. 3D geometry is an incredibly rich and vast space that is not yet well treated by artificial intelligence and machine learning. So one of our big projects is converting 3D data into other forms of information that you can actually do data science on. And by data science, I include machine learning. I mean, machine learning is just kind of like fancy statistics. So I include AI and machine learning in that capture. But the point is, how do we get 3D information into a format where it can be where there can be a meaningful intersection with ML and AI? And so we have customers who are working on exactly this kind of thing, creating large data sets or working on their own historical CAD data sets to try to extract important historical insight or design insight from it. And I think that's a really exciting place that geometric intelligence will be applied.
Interesting, interesting. Just one more quick one for you, and then I'll close out. So, with advances in computational geometry, uh, what do you believe will have the biggest impact on CAD in the next decade?
Yeah, I mean, AI might be getting there, but actually I think more maybe something that is often missed is that the way we represent 3D geometry on a computer, it's not obvious or natural, right? There's a few different ways to do it. And historically for CAD, there have only been maybe a handful of different approaches. Metafold takes a genuinely different approach to representing shapes. And I believe that, and we're not alone in this, I believe that these kind of new approaches to representation of geometry will open doors to new kinds of design. This is certainly true in additive manufacturing, where you have higher complexity structures, and just new opportunities to design more flexibly, to design new kinds of things. And I'm like super excited about what the future holds for CAD.
Interesting. And we're at the 1 hour mark, so I would like to thank all of our panelists and thank you, Elissa, for answering those questions. But just amazing conversations, amazing insights from everybody today, from Mark, from Max, and Elissa. So, I mean, really a huge personal thank you from myself, but from all of us at Design Engineering. It's amazing everything that you shared. to our audience today, a big thank you to all of you. I know some questions started coming in right at the end. Anyway, we'll try to get those answered and perhaps have a follow-up report in as an addendum to this session. But we need to be respectful of our speakers' time. So again, thank you, audience, for participating. And if you missed any of today's session, that's okay. It has been recorded, and we'll notify everyone when it's ready for viewing. Meantime, again, thanks to all of you from all of us at Design Engineering. Bye for now.